Good morning, good afternoon, and good evening, everyone. I'm John Storpett, the Principal Director for Marine at the International Chamber of Shipping, and I'm delighted to welcome you all to this ICS leadership briefing. Onboard carbon capture and storage, or OCCS for short, is gaining a lot of traction as a potential pathway for both new builds and existing ships to achieve compliance with greenhouse gas regulations. In response to requests from our members for updated high-level strategic guidance on the evolving OCCS landscape, we commissioned Lloyd's Register to provide a comprehensive study, and I'm pleased to be joined today by the authors of that report, which is due for publication next week, and they will guide us through their findings shortly. Before I do the formal introductions, I'd just like to remind everybody online that the discussion is being recorded and will be made available to registered participants after the meeting. We actively encourage you to participate by asking questions using the question function on your control panel. And thank you very much to all of you who've already submitted questions in advance. We've had a huge uptake in interest in this subject. So over to our panel. First, I'm delighted to welcome my colleague, Chris Waddington, who's the ICS Technical Director. Welcome, Chris. Next, a warm welcome to Yason Kontokristos, the Marine Performance Services Technical Specialist, Lloyd's Register Advisory. Welcome, Yason. Next, an equally warm welcome to Emil Shivachev, Technical Consultant at Lloyd's Register Advisory, and welcome, Emil. And to complete our panel today is Olympia Tsitonaki, the Maritime Decarbonisation Specialist at Lloyd's Register. So welcome, Olympia. So to kick off, Chris, if we could perhaps start with you, could you give us just a brief overview and perspective on OCCS from ICS? Over to you.
Thanks, John, and good day to all. In 2023, the International Maritime Organization revised its greenhouse gas reduction strategy for international shipping and adopted the key objective of net zero greenhouse gas emissions by or around 2050. To achieve this, IMO has adopted progressive measures to improve the fuel efficiency of ships and is developing a package of midterm measures which we hope can be agreed at MEPC 85 in November this year. To achieve net zero, a progressive uptake of the alternative fuels will be necessary, but the availability of these is currently poor and demand is expected to substantially exceed supply for the foreseeable future. Therefore, for the medium term, ship owners are considering what alternative technical measures are available. And onboard carbon capture and storage, also known as OCCS, shows potential, with some variants having achieved a high technology readiness level. IMO is currently developing a regulatory framework for OCCS with a target completion date of 2028. Therefore, at this point in time, it's important for ship owners to further develop their understanding of the OCCS options. And as John mentioned, our member associations urged the ICS Secretariat to commission a study with the objective of providing high-level strategic guidance to ship owners on the potential for OCCS to contribute safe, feasible options for GHG regulatory compliance. It's been a privilege to work with Lloyd's Register's experts on this study. Their report outlines the spectrum of technological options and provides a comprehensive assessment of the regulatory landscape. It addresses many of the questions that our member associations have been asking and provides an excellent starting point for those ship owners that are considering these technologies. I'm grateful to the Lloyd's team for providing today's webinar, and at this point, hand back to you, John. Thank you.
Thank you very much, Chris. I think that really gives us context for the discussion today and outlines the ICS members' interest in this technology, where it might fit in the overall decarbonisation strategy. So now that we've had that introduction, Olympia, could I now turn to you for Lloyd's Register's presentation.
Of course, John. Good morning, good afternoon, good evening, everyone. Thank you for joining us today, and thank you, Chris, for your kind words. It was been lovely to be working with you to produce this report. So, shall we please move to the next slide? And without further ado, jump to the agenda for today. So, I'm going to start by giving the first part, the description of the onboard carbon capture technologies. It's going to be presented by my good colleague Emil. Then we're going to be presenting the disposal pathways that I will be doing, and then we'll go to Iason to have a review of the regulatory framework around carbon capture. Closing in the end, we're going to close with the conclusions of the key findings that we're all going to discuss. So next slide, please. Before getting into the technical side, I just want to take a step back and answer a simple question, or at least try to. Why are we even considering onboard carbon capture? So we all know shipping is a hard to abate sector, and despite all the momentum around alternative fuels, vessels will continue to emit well into 2030s. Mid-life vessels are under compliance pressure. The regulatory and carbon cost pressure is also increasing with mechanisms like EU ETS, Fuel EU Maritime. On top of that, fuel uncertainty does exist. Even though alternative fuels are developing, they still face challenges in availability, infrastructure, and cost. Therefore, the transition is not happening uniformly or fast enough. On top of that, CO2 transport, storage and utilization markets emerge, particularly in the European area and the US. Therefore, we see onboard carbon capture as a potential pathway to reduce reported emissions. And therefore, I would like, with that context in mind, return to my good colleague Emil to present his part on around technology landscape for onboard carbon capture technologies. Thank you.
Thank you, Olympia. Next slide, please. So in this section, I will talk about the onboard carbon capture storage technologies. First, I'll start with the overall structure of marine carbon capture ecosystem. So at highest level, capturing carbon on board follows a common chain, and the capture is the starting point. And after the capture, carbon must be processed and handled on board, typically stored temporarily, and eventually removed through offloading and discharged to a shore-based or offshore facility for permanent storage. So each part of the carbon capture system is essential for this shipboard CO2 management, and it's designed to work together. There are two main technical approaches to capture. The first is a pre-combustion method, where CO2 is separated from the fuel before it's burned. This typically involves LNG fuel reforming or thermocatalytic processes to produce hydrogen and CO2. This system can be efficient in theory, but it introduces high complexity and significant integration challenges on board, and it's only applicable to LNG fueled vessels. In the more currently far more relevant approach is post-combustion capture. Here, CO2 is removed from the exhaust gases produced by engines on board. So for now, we'll mostly focus on these post-combustion technologies, and as these represent the most realistic near-term pathway for shipping. Next slide, please. So here we have post-combustion carbon capture technologies. At the top level, chemical absorption stands out as the most mature and widely deployed option so far. This method typically used amine-based solvents to selectively capture CO2 from exhaust gases. It requires elimination of SOx and particles before capturing the CO2. And also from a marine perspective, these key strengths of this method are proven performance, high capture efficiency, and also compatibility with retrofits, as it doesn't require engine modifications. However, it requires a higher energy demand and space requirements related to liquid CO2 storage and also solvent management. Membrane separation is also often discussed as a compact and modular alternative post-combustion capture method. Here, CO2 is separated through selective polymer membranes, which avoids chemical solvent handling. However, membranes are sensitive to exhaust impurities, moisture, and high temperatures, and generally have lower capture efficiency. And this technology remains low to medium at TRL so far. Again, physical separation use solid sorbents to trap CO2 on the surface of solid materials. This system offers good modularity again, but sorbent degradation and requirement of multiple absorption beds for continuous operation limit the marine applicability, and hence it has low to medium TRL so far. For cryogenic separation, the CO2 is removed by cooling and condensation. The main advantage here is that the production of very high purity CO2 without any chemical solvent handling. However, there are electrical power demands and refrigeration complexities are substantial, and this method again is mainly viable for LNG fueled vessels with available cold energy. Finally, calcium looping and mineralization involve reacting CO2 with calcium-based materials to form a stable solid called limestone, and this method avoids pressurized or cryogenic liquid CO2 handling and offer high capture potential, but again, it introduces solid handling, disposal challenges, and some operational complexity. However, pilot studies so far for calcium looping show significant promise, but large-scale shipboard integration is still at the development stage. Next slide, please. So in this slide, we'll look into operational suitability between liner and trunk shipping, how these different capture technologies align with real shipping operations. Liner shipping is generally far more suitable for early OCCS adoption than trunk shipping, as these liner services operate on fixed schedules, predictable port calls, and repeated routes. Hence, it makes it easier to arrange CO2 offloading, infrastructure alignment, and long-term logistic agreements. For trunk vessels, with their irregular trade patterns, they face significant challenges securing reliable CO2 offloading and handling arrangements at ports. So chemical absorption systems are best suited to liner shipping, where on these major hubs that they operate, investment in CO2 handling and offloading infrastructure can be justified, and space requirements on board can be managed also through a careful feasibility study. However, for trunk vessels, the picture is different. The effectiveness of the amine-based system is again limited by the availability of offloading port. If the ship cannot offload the captured CO2, this becomes dead weight, and lack of widespread CO2 reception infrastructure makes it less attractive for trunk shipping sector. For membranes and solid absorption system, Again, the offloading infrastructure still limit their applicability, even though this system may offer space advantages due to their modular and compact properties. The offloading requirements reduce the applicability for Trump sector. Cryogenic systems may work for very specific cases I've mentioned earlier, such as LNG carriers. So these are not really suitable for other large segment of Trump shipping, bulkers and tankers. Pre-combustion method, the thermocatalytic decomposition, may offer a kind of cross-segment applicability, but it still remains at early maturity. This could be an effective solution for both Trump and liner sector, as it produces solid carbon instead of liquid CO2. Hence, it doesn't require a specific cryogenic port infrastructure. This solid byproduct can be offloaded using standard bulk handling equipment in any port, basically. However, again, these technologies are in early stages. There is another method, an innovative method, is marine bicarbonate, which may be a promising future pathway for both segments as well. Again, in this process, limestone is reacted with CO2 from combustion to generate environmentally benign bicarbonate ions, which can be discharged into the seawater. As like this eliminates the CO2 storage and eliminates port dependence, and hence it can be a strong fit for Trump shipping sector. However, the big blocking point here is the regulatory approval, and there are no marine scale demonstration right now. It's still at the very early stages, and this method remains unproven and is subject to ocean discharge regulations. So the suitability of OCCS is highly dependent on the vessel's trading pattern, not only the capture technology itself. Next slide, please. So here I have the integration challenges and operational impacts. It's important to note that OCCS is not only about the capture challenge, it's a full system integration challenge. Onboard storage is one of the biggest constraints. Liquid CO2 tanks require significant space and add considerable weight, which affects vessels' stability and also available cargo carrying capacity. Like for every ton of CO2 captured, the required liquid volume is approximately 1.2, 1.5 cubic meters. So, and this liquid storage volume is strongly related to daily fuel consumption and the gross capture rate. Also, vessel type matters a lot here. Here we have an image from Maersk. It shows an oil tanker VLCC. They have advantage compared to other vessel types due to their extended deck space in the cargo area, which the CO2 tanks can be positioned. And also for new builds, these CO2 storage tanks can be incorporated in the early design stages. So achieving OCCS ready notations for new builds can be a way forward to feasibly accommodate these space requirements. Energy demand is another factor, as carbon capture introduces parasitic load on the ship's power system, and often leads to an increase in fuel consumption from 10 to 25%, even higher, depending on the capture rates. So potential implementation of waste heat recovery systems and evaluation and installation of PTO shaft generators can be investigated to cover for this extra energy demand. And finally, the port infrastructure readiness remains a major bottleneck. So far, only a limited number of ports can receive capture-based CO2. And ports need to offer flexible CO2 reception facilities to handle these diverse OCCS systems. So some mitigations measures for that would be maintaining high-level monitoring of OCCS developments, including LCO2 logistic routes, like green corridors where long-term agreements between charters and onshore handling facilities can be established. So the key message is that OCCS is technically feasible, but the success depends on careful vessel-specific integration and alignment with wider CCS value chain. And with that, I will hand it back to Olympia to talk about the CO2 disposal pathways.
Thank you, Emil. Thanks. So if you move to the next slide, lovely. Next slide, please. So carbon capture, utilization and storage refers to a group of technologies that are designed to capture CO2 emissions and prevent them from entering the atmosphere. So the process is quite straightforward. First, CO2 is captured on board, then processed, stored temporarily on board in dedicated tanks, and finally offloaded to either onshore or offshore facilities for further use or permanent storage. So once the CO2 is captured, it can be either utilized or stored. In terms of utilization, as we can see, it can either involve direct use, such as in industrial or agricultural processes, or conversion to products for synthetic fuel production, for example. Alternatively, CO2 can be stored in geological formations or used for enhanced oil recovery. Next slide, please. Perfect. So I would like to focus here on the fact that CCS is no longer about individual projects, and CCS clustering is a key point to move forward around the value chain of CO2. So what we do see here in the map on the left side of our presentation is that in the US, the model is largely pipeline-led with large integrated hubs concentrated around key regions. This system prioritizes, however, domestic capture and storage, which is supported by policy incentives, and the reliance to CO2 shipping is limited. In Europe and the UK, however, the approach is different and more infrastructure driven. There is an emergence in the North Sea in open access North Sea hubs, which are designed as shared CO2 disposal networks, and this enables obviously emitters, even cross-border emitters, to connect, making CO2 shipping a central part in the value chain. Reinforced, of course, from increasing bilateral agreements. Lastly, in the APAC region, the landscape is more fragmented, but momentum is also clearly building, with countries like Japan being in the forefront of these developments. Next slide, please. So the port interface here is where CO2 becomes operational, and it's basically the critical link between transport and final storage or utilization. So on the left side, when we're handling with CO2, liquid CO2, we have to keep in mind that we are dealing with a cryogenic liquid. So transfer from ship to shore requires controlled offloading with vapor return systems, or it's important to know that it's not a standard cargo operation. So dedicated infrastructure is required. And the key constraint we see is the CO2 quality and the fact that it must meet strict injection-ready specifications. defined by the storage operators. Now, if we compare this to carbon byproducts like solid carbon or carbonates, they're much easier to handle. They can use existing bulk or container port infrastructure without the need for specialized systems. Next slide, please. So having seen a bit the port interface, we would like to look at the economics of around the value chain of CCS. And when we look at CO2 offloading, transport and storage, the key point is that cost is not purely technical. It's driven by infrastructure and system choices. Starting from the left side with the capture, this is typically the largest cost component, as you can all see, and it's ranging from roughly 27 euros to over 100 euros per ton of CO2, and this depends largely on the source of the technology. So moving to transport, shipping is more flexible but comes at a higher unit cost. However, pipelines are even though they're most cost efficient, they require upfront infrastructure and scaling. Finally, storage costs depend heavily on geology. Depleted gas fields are generally lower cost. Saline aquifers can be more expensive. More importantly, the focus is what the market pays is not equal to the technical cost. The pricing is shaped by who's willing to take the risk, how is the long-term liability, or what are the financing structures, and what is the maturity of the storage market. And when we break it down, what actually drives cost, it comes down to system level factors like CO2 quality and conditioning requirements, pressure and temperature misalignment across the value chain, the utilization rate, and critically storage readiness and regulatory liability. Thank you. May I pass on to my colleague Emil now to the next slide. Thank you.
So thank you very much, Olympia. Hello, everyone. Let us just go to the next slide and start for this part of the presentation. So up to this point, we have heard how onboard carbon capture actually works and what can technically be done with the CO2 once it leaves the ship. However, what ultimately determines whether OCCS can move from pilot projects to real deployment, it's not technology, it is regulation. So in our study, we have analyzed 4 key pillars as major contributors to the regulatory framework allowing or restricting the adoption of OCCS. Firstly, the IMO regulatory framework. So IMO is largely considered to be the most important stakeholder since a unified scheme would be needed for the creation of a global OCCS value chain. Then we have the EU regulatory framework. EU instruments already provide economic signals and incentives for innovative technologies. For OCCS, this creates a near-term opportunity, but also it creates regional complexity for vessels operating globally. Third, we have environmental conventions. Those govern the movement of loading and disposal of CO2 and its derivatives. They are essential for enabling a cross-border CCS value chain, but of course they also introduce legal boundaries. And finally, we have classification societies. So in today's regulatory gap, class plays a critical bridging role, providing the only practical pathway for OCCS installation to move forward safely until formal regulatory frameworks are evolved. Let us go to the next slide, please. So starting off with IMO's short-term measures, we have EDI, NTXI on the design side and CII on the operational side. Under the current framework, OCCS technologies are not recognized in the calculation methodologies for EDI or EXI. For OCCS to be included, the XI guidelines would need to formally recognize carbon capture as an approved emission reduction technology. That would require agreed assumptions on a by design performance profile under reference conditions for OCCS systems, and all extra energy requirements would need to be accounted for. For the time being, there is no specific methodology available. Now, turning to CII, the situation is similar. CII is based on fuel consumption reported under the IMO DCS and currently reflects gross CO2 emissions at the point of combustion. So there is no mechanism to recognize captured, stored, or offloaded CO2. CII in general contains a large amount of correction factors to reflect specific vessel operations, and that could potentially benefit the accounting of OCCS effect. The formal procedure of transfer of legal responsibility from ship to shore and then to store facilities would need to be created. A relevant certification procedure would need to be developed. For the time being, none of that is available. However, the DCS regulation allows for direct CO2 measurements, which is something that could be beneficial for future OCCS crediting. Next slide, please. So OCCS could play a significant role in achieving IMO's mid and long-term decarbonization targets once a proper regulatory framework is set. The net zero framework has been adjourned for a year. However, it is fair to say that the adoption of OCCS could very much align with the targets of the regulation. In the graph of this slide, you can see the IMO NZF base and direct limits, as well as the zero or near zero energy source limit. Now, the dotted lines represent the greenhouse gas intensity of common marine fuels like HFO, MDO, and LNG. Now, if we move to the next slide, you will notice that those lines have moved downwards, and that reflects the impact on the intensity of those fuels if an OCCS system with a 30% CO2 capture rate is used on board a ship. According to the latest updates, OCCS has been formally acknowledged as a pathway to be included in the regulation by crediting the CO2 emissions that are successfully captured on board a vessel and delivered for permanent storage. The methodology would align with IMO LCA guidelines and the relevant factor created. For the time being, the detailed methodology for accounting and verification is under development. Next slide, please. So we will now move away from IMO and approach EU's regulatory framework. So EU has made major steps towards accounting of OCCS, even though some asymmetry between regulations can be seen. For the time being, EU ETS is the only regulation that allows for OCCS crediting, provided permanent storage is possible in accordance with EU carbon capture and storage framework. It is noted that even though ETS provides the way forward for immediate OCCS crediting, no relevant cases have been observed yet. In contrast, under FuelEU Maritime, OCCS is currently not addressed within the existing methodology, since FuelEU actually stands for the adoption of alternative fuels, and OCCS could potentially extend the life of fossil fuels. Despite that, the FuelEU regulation offers opening for future consideration as OCCS could become a key enabler for biogenic and synthetic renewable fuels, again, once a long-term sequestration and sufficient maturity of monitoring and verification systems are provided. Let's move to the next slide. Thank you. So having looked at global and regional regulation, we will now zoom in on a national level in national initiatives which are becoming increasingly decisive for whether OCCS can actually be implemented in practice. What we see very clearly is that Northern Europe currently leads in the creation of a functioning CCS value chain. A number of transnational agreements are already in place from 2024, just like the multilateral agreement between Sweden, Denmark, Belgium, and France with Norway, where Norway could receive and store captured CO2 from the other nations. Denmark has also signed 2 bilateral agreements, one with Sweden and one with France, enabling cross-border transport and storage of CO2. For all the mentioned cases, the transportation of CO2 will be done through ship, at least for the first stage. Also, the US is considered a jurisdiction with a major framework regulating CO2 capture and storage, even though international CO2 receipt remains constrained. Asian countries like Japan, China, and Singapore are regional leaders in OCCS-related regulatory development. Next slide, please. So zooming out again, we will discuss on the international framework governing the movement of captured CO2, which for the time being remains fragmented and unclear. So starting with the London Convention and the London Protocol, which regulates the dumping of wastes and other matter at sea. Amendments adopted in 2006 explicitly allow sub-seabed geological storage of CO2, but initially prohibit cross-border exports. A further amendment in 2009 enables the export of CO2 for offshore storage. However, for the time being, the amendment has not entered force, lacking the needed support from member states. As a temporary solution, the parties adopted a 2019 resolution allowing provisional application of the amendment, provided a bilateral agreement is in place. In parallel, the Basel Convention governs the transboundary movement of wastes and their disposal. Here, the classification of captured CO2 becomes decisive. If CO2 is categorized as waste, prior informed consent procedures apply, while if captured CO2 is classified as hazardous waste, certain movements may be completely prohibited under the ban amendment. It should be noted, however, that the application of Basel Convention to the case of captured CO2 remains conditional and under a number of scenarios that yet remain uncertain. Let's go to the next slide now, please. So finally, we focus on the role of classification societies, which today are playing the pivotal role of enabling early OCCS deployment. At present, there is no harmonized global OCCS code, no unified design criteria, and only limited prescriptive safety requirements. In addition, alignment with port reception and offloading rules remain incomplete. So in this regulatory context, classification societies are effectively acting as a bridge between innovation and regulation. Through risk-based design approaches, early hazard identification and hazard inoperability studies, and the use of approvals in principle, CLASS provides structured and credible pathway for OCCS systems to be assessed and installed safely. Regulatory gaps can also be covered through the selective application of IGC code, IGF code, and SOLAS regulatory parts where relevant, and at the same time, work is ongoing within IACS to develop more unified requirements, which can eventually support the transition from case-by-case approvals to more prescriptive rules. Let's go to the next slide. So right here, I would go back to Emil to start with some conclusions and key findings of the study.
Thank you, Edson. Next slide, please. So I will. Here we have the key integrated conclusions from all our 3 parts of the presentation. I'll start with the top left from technology readiness and go clockwise. And regarding technology readiness, as you've seen, these levels vary widely, and most concepts remain at pilot demonstration stage. Very low commercial implementation so far. Chemical absorption systems are the most mature, followed by calcium looping methods. And these are the most deployable options in the near term. On the vessel integration part, as I've mentioned, there are significant challenges. The viability of OCCS depends on the vessel type, the trading patterns, available space on board, onboard energy margins as well. So we believe that in the early stages, larger and kind of energy-rich vessels are most viable early adopters for the OCCS systems. And over to you, Olympia.
Thank you, Emil. So going to the CO2 value chain, we do see that without the full chain in place, capture on board has no real impact. The biggest constraint is not technology, it is infrastructure at the moment, and ports and hub being emerging key bottlenecks. Therefore, what we need is CO2 reception facilities at ports, connections to transport networks, whether pipeline or shipping, and access to certified and standardized storage sites. At the same time, geography and hubs are also critical. The North Sea is currently the most mature ecosystem with established storage sites, developing CO2 transport networks, and regulatory frameworks that are also in place. But Yasun can expand further on this and give us his opinion and views.
Yeah, sure. Thank you. So from the regulatory perspective, indeed, it looks like the wider picture is really fragmented. So it looks like short distance transportation of captured CO2 is the most feasible way forward with the use of bilateral agreements. So we probably would see the creation of regional CO2 storage hubs. As Olympia mentioned, the North Sea leads in the field, while other hubs in Southern Asia and also the Mexican Gulf region might follow. Now, on the regulatory side of things, it looks like OCCS is a solution to be included in various environmental regulations and has the potential to aid the decarbonization target of the regulators. However, instant recognition is currently limited only to EU ETS. Having said that, several regulations are expected to adopt OCCS accounting once the barrier relevant to monitoring are resolved and accounting methodologies are developed. So taking everything into consideration, we can conclude that OCCS in general is a niche but emerging technology. The market is not yet established, but there is a clear appetite for investment and upscaling. On the regulatory side, things are not solid, but there is continuous progress. Those facts would lead to the conclusion that there is a significant opportunity around the field. Involvement in pilot projects and early adoption would be a sound decision for innovative players. Early actions to engage with the full value chain and the stakeholders might prove to be beneficial. And of course, monitoring closely the regulatory and legal updates would be needed to minimize risks. And that concludes our analysis. So back to you, John.
Thank you, everyone, for a very, very comprehensive summary. There's an awful lot to take in there. Don't worry, for those online, we will provide the slides afterwards, along with the recording of the session, and everybody who is subscribed to this webinar will get a copy of the study as well when it's published. We have a lot of questions and not very much time to get through them all. So I'd like to field some of those now. Firstly, Emil, there's been a lot of interest in the size of the OCCS that can be installed on board a ship. What are the space and weight requirements, or the space requirements and the weight characteristics of these systems, and how much volume do they take up on board?
So thank you for the question, John. It's a good question. So actually, it mainly depends on the target capture rate and the vessel's operating profile. Actually, the space requirements are based on the capture rate. If you are targeting a higher capture rates, and depends on the carbon capture system that you are utilizing. So how much the owner is willing to compromise on space, power, and capture efficiency, this will all affect actually. So there's not like a single answer that I can give you right now. Like this is like exact, but we are kind of seeing that it takes for chemical absorption-based methods, you'll need to have 2 to 5% of the dead weight of the vessel. Kind of you'll need to spare for the space requirements related to LCO2 storage on board.
Thank you very much. Olympia, if I could come to you, you touched on how developed, or where the leaders are in establishing the infrastructure that's needed for this. How developed are, or cost effective, or how developed are the cost effective ideas for the disposal of the captured carbon? And can we make this ocean friendly and benign? You're on mute, Olympia.
Oh, sorry. So touching on the disposal pathways. So on a cost-effective level, disposal pathways are still developing, and at the moment, the most famous and widely used is permanent geological storage, especially under the seabed, where CO2 is injected beneath the seabed in stable formations. This, of course, is not. It is an ocean-friendly process. On a more benign alternative, so a mineralization process, where basically we're converting CO2 into limestone, is an emerging solution, and it can provide stable and low-risk products. But of course, we have to keep in mind that they remain at an early stage and limited scalability.
Thank you, Olympia. And yes, you did touch on this in your slides, but do you anticipate that IMO will recognise utilisation as an eligible measure for CO2 emission reduction?
So thank you, John, for this question. So actually, according to the LCA guidelines, carbon capture and utilization is in a middle ground. Unlike carbon capture and storage, utilization does not necessarily remove CO2 permanently from the carbon cycle, but reuses captured CO2 to make synthetic fuels, chemicals, or materials that they might later re-emit CO2. There is ongoing work on the development of an accounting methodology for carbon capture and utilization, considering relevant frameworks such as IPCC guidelines.
Thank you very much. Obviously, this is a new technology, and one of the key work streams at IMO in the context of alternative fuels has been training for seafarers in using them. And I wonder, what training do we anticipate that seafarers are going to require in order to operate these systems? Emil, I don't know if you have any views on this.
Yeah, I can cover that. So Yes, it's a new system, and crews will need training on these new systems, which will be probably integrated into the control room operations and also for the maintenance schedules on board. While we expect the systems will be like largely automated, our crew training like on basic troubleshooting will be essential. And also crews will need, I think, specific training regards to the like liquid CO2 offloading operations. So far, like safety standards for the OCCS equipment and procedures are incomplete, and the training requirements for crew that are handling OCCS systems are currently lacking. And crews' unfamiliarity with these systems may lead to like operational errors and emergency conditions. So for crew, training will be essential. For some vessel segments like LNGs, the crews are kind of familiar with this effluent gas handling procedures, but for wider vessel segments, yeah, the crew training will be definitely required.
Thank you. So it's clearly something we need to get a handle on very, very soon if we're to make this a realistic solution. As we look ahead, obviously we're at the start of this journey, but what do we think an end-to-end OCCS value chain looks like 5 years from now, particularly with respect to the commercial viability and the applications that can be made for the captured carbon? Olympia, what are your views on that?
Okay, I can try to capture this. What we would expect is that in 5 years we would have a more evolved and hub-based end-to-end carbon value chain system. We would expect to have like CCS carbon capture hubs in areas like we've seen in the North Europe, like we've seen in the UK. We would expect something similar to try to be simulated in the Asian Pacific regions, and basically we have at the same time LCO2 shipping being an integral part for CO2 transportation. But of course, commercial viability will heavily depend on carbon pricing and whether regulatory recognition of the captured CO2 is going to happen. So that would be my take on this.
Thank you, and I'm glad you mentioned hubs, because I think it's really important to emphasize, particularly to regulators, the need to get ahead of investing in infrastructure now to make these solutions viable. We see it with alternative fuels, and I think this is another area where we really need the decision makers to recognize why it is essential to invest in their port infrastructure to make these solutions feasible. We are running slightly out of time, but just before we go to conclude, one final question, Yasin, for you, if I might. What do you see the major issues that will be or are that to prevent this technology from progressing? Are they predominantly regulatory, or are they financial and commercial?
Okay, thank you. That's a very interesting question. I think it's also a bit tricky. So, in my point of view, when we look into regulatory and financial barriers, we are actually looking at the same problem from different viewpoints. So, there are currently regulatory barriers, and there are financial challenges largely stemming from this uncertainty. So the technology itself is progressing, but OCCS is not yet fully recognized under key frameworks, key regional regulatory frameworks. The result of that for ship owners is uncertainty. So this lack of certainty that captured CO2 will translate into compliance benefits or economic value poses investments. So once clear rules exist, in my point of view, investments would follow, particularly in regions where carbon pricing and OCCS infrastructure already is in place.
Thank you very much. Okay, we're reaching the end of our discussion today, so I'd like to give each of the panel members just 1 minute, and I will restrict you to a minute because time is pressing, to give us just the 3 key takeaways on what messages they'd like our audience members to remember from your parts of the presentation. So, Yasin, can I start with you?
Of course. Okay, so 3 key takeaways. Firstly, I would say that OCCS is technically viable, but constrained at the moment, as the regulatory landscape is fragmented, but also evolving. Classification societies certainly provide a critical bridge to deployment. So that would be my number 1. A second takeaway, in my point of view, we shouldn't treat gaps in the OCCS process as dead ends. Technology solutions, regulatory framework, and investment in infrastructures and the whole value chain will all mature simultaneously and in parallel. So instead of seeing the gaps in one of those pillars as a dead end, we could consider that evolvement in one of those pillars would definitely lead to updates in the others as well. So that would be the second one. And my third takeaway would be that OCCS should be seen as an investment in regulatory preparedness and flexibility, enabling ships to adapt to future climate rules rather than standalone immediate compliance fix. Of course, OCCS is able to drive decarbonization and help ship owners and vessels comply with the limits. But of course, OCCS should also paired with other decarbonization solutions and with a more holistic and long-term decarbonization strategy.
Thank you. Olympia, what are your 3 takeaways?
Okay, so on my side and from my spectrum, I'd say that disposal is not the main constraint, integration is. So storage solutions exist, but the real challenge is basically connecting capture, transport, and storage into like a fully integrated value chain, particularly at the port interface, which is, as we have said multiple times today, it's the key bottleneck. And explicitly around port interface, I would say the infrastructure status for offloading is currently the weakest link. Limited ports can handle capture grade liquefied CO2. And of course, even though infrastructure exists, it is not deployed at scale. So developing a standardized protocol and procedures, and as well as safety frameworks and investment, are of key importance. And last but not least, as I've said, like CO2 hubs are going to be the key pillar for the whole integration. So, and LCO2 shipping will be the backdrop for this, and will enable onboard carbon capture to scale across regions.
Thank you. And Emil, very quickly, because we have just over a minute left.
Yeah.
3 takeaways.
Okay, so firstly, OCCS is technically feasible today, but it's not a one-size-fits-all solution. The viability of OCCS depends on the vessel type, trading pattern, like available space on board, onboard energy margins. So the technology choice must be aligned with how the ship operates. And OCCS technologies have successfully demonstrated in pilot projects, but the readiness across the various technology is various. So chemical absorption systems are most mature with capture rates up to 90%. Cryogenic capture, calcium looping may offer also potential advantages, but they remain at lower readiness levels. So, and finally, OCCS can play a meaningful role in the decarbonization of the shipping industry, but successful deployments will depend on the whole carbon capture storage utilization infrastructure. Thank you.
Thank you. Thank you very much. Right, I have 5 seconds. Thank you, everybody, for a great presentation and a really important topic for us to consider. Before we close, I'd just like to remind everyone that the next edition of the Leadership Insights webinar series on marine applications for batteries will be held on the 5th of June at 1200. Thank you, everybody who has contributed, our distinguished authors, and Chris, who initiated this work stream from ICS. We appreciate the time you've taken to join us today. And with that, I think we could sign off. Thank you very much, everybody, and have a good rest of your day.
Thank you. Thank you very much.
Thank you.